Welcome to Week 10, Convolutional Neural Networks or CNNs. Here, on day 1, we'll be looking at Introduction to Convolutional Neural Networks. Day 2 will cover convolutional layers and filters. On day 3, we'll be looking at pooling layers and dimensionality reduction. Day 4 will cover building CNN architectures with Keras and TensorFlow. Day 5, we'll be looking at building CNN architectures with PyTorch. Day 6, we'll be looking at regularization and data augmentation for CNNs. And finally, for day 7, we'll be doing our CNN project, which will be an image classification on Fashion MNIST or Cypher-10. So let's get started with week 10. Welcome back to week 10, where our first day, we're going to look at Introduction to Convolutional Neural Networks. Let's first dive into overview of CNNs or convolutional neural networks and their role in image processing. Now first, let's cover what are convolutional neural networks or CNNs. CNNs are a specialized type of neural networks designed for processing structured grid data such as images. They are particularly effective for image-related tasks like classification, object detection, and segmentation. Why CNNs for image processing? Spatial hierarchies. CNNs capture spatial and hierarchical patterns in images. Convolutional layers extract features like edges, textures, and complex structures. Also, parameter efficiency. Unlike fully connected networks, CNNs use fewer parameters due to shared weights, reducing computation and memory requirements. Next, let's look at the CNN architecture. Some of the key components of a CNN are convolutional layers. They perform convolutional operations to extract features. Then it has kernel or filter, which is a small matrix, example 3 by 3, that slides over the input images to detect patterns. And then we have the output. The feature maps highlighting specific patterns in the input. Next, we have the pooling layers. They downsample feature maps to reduce dimensions and computation. The types are max pooling, which takes the maximum value in a region, and average pooling, that takes the average value in a region. Fully connected layers. They combine extracted features for final prediction and act as a classifier in the network. The basic CNN workflow is you pass the input image, it goes through the convolution, next activation, then pooling, then fully connected layer, and then you get the output. So some of the key advantages of CNN over the fully connected network for images are, first one is the translation invariance, where CNNs can detect patterns irrespective of their position in the image. Reduced parameters. Shared weights and local connectivity make CNNs computationally efficient. Automatic feature extraction. CNNs learn to identify meaningful patterns like edges, shapes, and textures directly from data. With all this in mind, let's jump into our hands-on exercise where the objective is to visualize images in a dataset, explore their pixel data, and set up an environment for building CNNs using TensorFlow and PyTorch. So first step is to visualize images in a dataset. So I'm going to go ahead and create a new file, not a Jupyter notebook. Try again, Python file. Save this file. In week 10, day 1, I'm going to call it day 1 underscore exercise. First, let's go ahead and since we are plotting, I'm going to get matplotlib.pyplot as PLT. Since this is our first video of the week, I'm going to go each and every line in detail. So this imports the pyplot module from matplotlib, which is used for creating visualizations such as charts and plots, and that's why we are using it. And then next, I'm going to say from torch vision, import datasets and transforms. So what I'm doing here is this thing imports datasets and transforms from the Torch Vision library. Datasets provides access to the popular datasets like Cypher-10, which we are going to use, or MNIST, and others. Transforms contains utilities to pre-process and transform image data, such as converting images to tensors. So now let's go ahead and load our data set. I'm going to say transform equal to transforms dot to tensor. There you go. So this line here defines a transformation to convert images from the dataset into PyTorch tensors. This is necessary for using the data in PyTorch models. Next, I'm going to say train underscore dataset equal to datasets. This is what we picked up above, but I am going to use cipher 10 root equal to dot slash data. And again, I'm going to explain as soon as I write this. First step is to write this code. Train equal to true, transform equal to transform that I created above, and then download equal to true. So we have seen this before, but I'm going to go over this one more time. This loads the cipher 10 dataset. Now the cipher 10 is called cipher 10 because it kind of classifies all the images into 10 different things from 0 to 9. 0 is for airplane, 1 is for automobile, 2 is for bird, then cat, then deer, dog, frog, horse, ship, and truck. You can Google that thing and you can find the different parts. But here, what I'm doing is I am saying that I want a cipher10 root dot slash data where specifies the directory where the dataset will be stored. Train equal to true loads the training split of the dataset. Transform equal to transform. This applies the transformation to tensor to the images, and download equal to true says that download the dataset if it's not already present in the specified directory. I don't have this data, so it will download the first time. Next, I'm going to go ahead and visualize sample images. To do that, I'm going to say FIG and axis. These are the two variables that get pulled in from PLT dot subplots 1 comma 5 comma fixed size equal to 12 comma 3. I know we have worked with some of these things, but what does this all stand? This creates a figure with 1 row and 5 columns of subplots for displaying images. The fixed size defines the size of the figure, which is 12 by 3. So it will be 12 inches wide and 3 inches in height. So that's what we'll get as an output. Now, next I'm going to go ahead and run a for loop for I in range of 5. I'm going to say image, comma, label equal to, I'm going to pick my train data set and get the ith element from these 5 images that I'm getting. Axis of I. So this line, what it does is it loops through the first 5 images in the training data set, and for each image retrieves the image, and which has the image variable has the image data, and the label is the corresponding label to that particular image. So next I'm going to go and say axis I dot im show, and inside that say image dot permute 1 comma 2 comma 0. So in this particular line, what I'm saying is I'm displaying the image using IMShow. That's a function that shows the inside that function. I'm calling the permute method, which reorders the dimensions from channels, height, and width to height, width, and channels. So usually it's 0, 1, 2, but I'm saying 1, 2, 0 because I want to change from. I want to move the channels to the end. Height I'm going to move to the first, and then width I want to move to second. So this kind of moves them around and accordingly gets me my data. Next thing I'm going to do is axis of I dot axis. I'm going to set this to off. So here I am saying that hide the axis for a cleaner display of the image. Don't show the axis in the graph. Next I'm going to say axis of I dot set underscore title f of label and label. So in this particular case, I'm saying that set the title of each subplot to the label of the image. So that will make sure that it will show us what type, what category does it come into. And then I can say plot dot show. If I run this now, let's go ahead. I'm going to say Python day one underscore exercise.py. First, it's going to download the images. So I'm going to let it download and come back to it once it's ready. It might take a little bit time. But until then, we can go ahead and explore the pixel data. So for that, I need first of all import numpy as np, and then I'll say display pixel values for, let's do it for the first image. Now here I am going to say image comma get me the data image. Oops, there you go, the images are showing up, but I'm going to just complete this first. Image comma label equal to train data set. From that I want the element 0, and then I'm going to say print f of label equal to label, whatever that label is for the first element. I'm going to say print f of image shape equal to image dot shape. Next I'm going to say print pixel values, and then I'll print the image. So that's, so what I'm doing here is this displays the pixel values for the first image. Image comma label line number 19 train dataset retrieves the first image and its label from the training dataset. Next, I print the label of the first image. Next, I am printing the shape of the image tensor, typically 3 by 32 by 32 for cipher 10. That's what is used, representing 3 different channels and 32 by 32 pixels. And then finally, I am saying print the pixel values, and I print the tensor representation of the pixel image values here. So let's go and look at the output. Here is our plot where we have 5 different images. The first one looks like a frog, which, as I mentioned, belongs to label 6. So that's the 6th element. Then this looks like a truck and this looks like a truck. So these are both trucks which belong to label 9. That's the last one. And label 4 is, I think it's deer. So that looks like a little bit of deer. I don't know if it's deer or cow, but it's one of them. And then this one is automobile, which is 1. So this looks like it was able to display. Now for the next part that we have here, of course, if I open my folder, I will see that I have this data folder which all the cipher 10 images inside here. It's probably a big file. If you look at just the zip file, is 170 MB. And then I have my day one. This is my code. So I am going to go ahead, clear this, and run it one more time. This time it will not download because I have already downloaded the files. And I'm going to close this. So it shows me the image label 6. This is for the first one, which was, I think, frog. And image shape, this is the image shape. And this is the pixel values. This is how the tensor looks like. And this is the image representation in tensor. Our next step is to set up an environment for building CNNs. So we'll be setting up for both TensorFlow and for PyTorch. So first, let's go ahead and I'm going to clear this out. Make sure you have TensorFlow installed. It doesn't hurt to run Tensor, if I can spell it right, TensorFlow. If you've already installed it, it'll be pretty quick. So I'm going to clear that out. So that kind of has my TensorFlow. Now, if I want to, I can go ahead and comment these things out. I don't need that. And to just to run a basic TensorFlow application, I'm going to say TensorFlow as TF. Next, I am going to say, I'm going to define a simple CNN model. To create this model, I am going to say model equal to TensorFlow dot keras dot sequential. I have not imported that yet, so that's why it's not showing up. but this is because I can just have them on, so then it might not give me a warning. Next, I need inside here tf dot Kara. So again, let's go over each line. This one imports the TensorFlow library for building and training deep learning models. This one here, what I'm doing is I am defining a simple convolutional network, neural network, the CNN, where first I need to create a layer. So this is a sequential model, which means each layer is run one at a time in sequential order. So first layer is, as I mentioned in CNN, should be con2d 32 comma. So I'm going to give all these parameters and then we can explain over them. 3 by 3 comma activation equal to I'll use ReLU activation, and then I'll say image shape underscore shape equal to 32 by 32 by 3. Next is my next layer. So first layer is con2d, which is a convolutional layer with 32 filters. That's why 32 the number, a 3 by 3 kernel, and a ReLU activation for the image that we have. So that's what is my first layer. That is what I'm defining there. My next layer, tf dot keras dot layers dot max pooling 2d. Now this one I can just pass 2 by 2. So this is a max pooling 2D layer with 2 by 2 pooling window to reduce the spatial dimensions of the previous input. Next, I'm going to flatten. So for that, I can say tf dot keras dot layers dot flatten. This function, it flattens the 2D feature maps into a 1D vector for fully connected layers. So that's, we have that. And then finally, I'm going to call the dense function. For the fully connected layers with 128 neurons, we need to run this 128 comma. So dense goes by, again, since I've not done the import of layers, I have to write the entire thing here. tf.keras.layer dense, and this is a fully connected layers with 128 neurons. A ReLU activation equal to ReLU. This is that layer. Okay, let's make sure this comma, extra comma is removed. And then finally, I would make another dense layer. So I'm going to copy this. And in this one, I am going to say I need one with 10 neurons, which is for the 10 different classification units we have in Cypher 10. And I am going to use softmax this time activation for classification in this particular case. So I have my model created. Once I have my model ready, next thing is to compile the model. Now to compile the model, I'll run model.compile function, and I'm going to use optimizer equal to Adam. I will say loss equal to sparse underscore categorical underscore cross entropy, and then I need metrics equal to, I'll set that to, can use multiple ones, but I'm going to just use accuracy for this one. So this is your model.compile function. What this does is this again compiles the model, but the configurations configures the model with optimizer of Adam, which uses the Adam optimizer for training. Loss equal to sparse categorical cross entropy specifies the loss function for the multi-class classification, and metrics is equal to accuracy, tracks accuracy during the training. So that's what this does. Now I can go ahead and say after this that my TensorFlow CNN model is ready. Let's go ahead and run this. Oops, not Python day one. So I'm going to just jump directly to that, and looks like con 2D image shape. Did I spell it wrong? It's input shape. That's why. Clear. Run it again. And it says TensorFlow CNN model is ready. It says that when using sequential model, prefer using input shape object as the first layer in the model instead. So instead of passing is to the con 2D, it says use input layer, but this is fine too. Just a warning. Next, I'm going to go ahead and show you how to do this for for PyTorch. For PyTorch, make sure that you have Torch and Torch Vision installed. So I'm going to run this pip install again. Pip install Torch and Torch Vision. So I have already installed that, so it should be there. So I don't have to worry about them. Next, I'm going to go ahead here and write the code for first. I'm going to import torch.nn as nn. Now this will import the NN module from PyTorch, which provides tools for building neural networks. So once that is done, let's go ahead and define a simple CNN model. To do that, I'm going to start with class simple CNN and pass it nn.module. Now I'm going to go over each and every line as I mentioned, because we'll be repeating this quite a lot, so I don't want to repeat this again and again. So pay close attention. So this code here defines a simple CNN model. I'm creating a class here which will define my module. And first thing, I'll go ahead and initialize this and write the initializer for this particular class. I'll pass the self object. This is the basic definition of initializer, where first I'm going to call the super class with the same simple CNN and pass self to it and say dot underscore underscore init, call that function. So first call the super. Next is I'm going to say self dot convolutional first layer equal to nn dot conv 2D. This is same as what we did for TensorFlow, but in PyTorch we're going to get it from nn. So nn.conv2d 3 comma 32 comma kernel size equal to 3 comma activation equal to value. Now this is more featured for our Python coding, so that's why it's made much more simpler, where what's happening is we're creating a convolutional layer with 3 input channels, 32 filters and a 3 by 3 kernel. So it's pretty straightforward as compared to what we did. We kind of had to spell everything out in TensorFlow, but in PyTorch it's much more easier. Next I'm going to say self dot pool equal to nn dot max pool 2d, and I'll pass 2 comma 2. Again, same as what we did with TensorFlow, we created a max pooling layer with a 2 by 2 pooling window. Next I'm going to say self dot fc1, this is nn dot linear, and I'm going to pass here 32 times 15 times 15 comma 128. So here we are creating a fully connected layer, transforming it from 32 times 15 times 15 into 128. And again, I'm going to use one more fully connected layer and call it fc2 equal to nn dot linear 128 comma 10. So what it does is now it's converting the input size to the output size. We're transforming 128 neurons and 10 classes. That's what's happening here. So that kind of takes us to the next point, which is creating the forward function self comma x. Now this defines the forward pass, where we'll have to first say x equal to f dot relu self dot conv 1 of x. So this applies convolution, con1 and relu activation. Next I need to apply the max pooling, which is x equal to self dot pool of x. Next I have to flatten the tensor using x dot view. So I'm going to say x equal to x dot view and pass it -1 comma 32 times same number as before, 32 times 15 times 15. So this will flatten the tensor. Next, I am going to call x equal to f dot ReLU self dot fc1 of x. So here I'm passing the data through fully connected layers of fc1, and next I'm going to do the same thing for fc2, where I'm going to say self dot fc2 of x. So these two last two lines passes the data through fully connected layers of fc1 comma fc2. So next thing is I have to mention, I'll say print PyTorch CNN model is ready. Let's see if it gives me an error. I'm going to run this. And as you see here, first it says TensorFlow CNN model is ready because I've not commented that. And then it says PyTorch CNN model is ready. So that's what we were expecting. So in this particular exercise, we did the visualization where we understand the structure and labels of the Cipher 10 dataset. Then we did pixel exploration where we gain insights into the numerical representation of the image. We displayed the image sizes and things here, right here. And then we did the environment setup for both TensorFlow and PyTorch for CNN development, which we'll be using quite a lot in the next few days. So stay tuned. So just to go over some of the outcomes from today, we understood the basic architecture and components of CNNs. We learned why CNNs are superior to fully connected networks for image data, and we gained hands-on experience visualizing and exploring image datasets. And we developed some foundational skills for building CNNs in both TensorFlow and PyTorch. So if you have any questions or had any issues or errors, let me know in the messages and I'll get back to you. Welcome to day 2, convolutional layers and filters. Today, we're going to jump into understanding convolutional operations, filters, and feature maps. So what is convolutional operation? A convolution is a mathematical operation where a small matrix, which is a kernel or a filter, slides over the input image to extract features like edges, textures, or patterns. Some of the key concepts include we have the kernel or the filter, which is a small matrix, example 3 by 3, used to extract features. Here, each element of the kernel is a weight learned during training. Next, we have feature map, the output of a convolutional operation, which highlights the specific patterns detected by the filter. Then we have channels. For RGB images, convolution processes each color channel separately and combines the results. Let's go over some of the concepts of kernel size, stride, and padding. So as per kernel size goes, the dimension of the filter example can be 3 by 3 or 5 by 5. Smaller kernels capture finer details, whereas larger kernels detect broader features. We have stride, which defines the step size of the filter as it slides across the input. Larger strides reduces the feature map size, improving computation efficiency, whereas smaller strides retain more detail but increase the computation, as you can make sense. Padding adds extra pixels around the input to control the size of the output. A valid padding is no padding, the feature map shrinks. Same padding adds enough padding to keep the output size equal to the input size. Next, let's talk about visualizing how convolution extracts features by edge detection. Kernels like Sobel or Privet highlight edges in images. Feature extraction. Initial layers focus on edges, deeper layers capture abstract patterns in this particular case. So, with this in mind, let's jump into our hands on exercise where our objective is to understand convolution operations by implementing and visualizing their effects using TensorFlow and PyTorch. So, first, let's go ahead and start with a new file, save it as day2 underscore ex. Now, first, let's go ahead and first we have to visualize the effects of convolution on an image. So I'm going to go ahead and import matplotlib as pyplot as plt. Then I'm going to import numpy as np, and then from ski dot nd image I am going to import convolve. That's what I need. So these three libraries, let's talk about them. So the matplotlib pyplot as plot imports the matplotlib.pyplot library, which is used for creating visualizations like plots and images. NumPy imports the NumPy library, which is essential for numerical computations and handling arrays. That's what we'll be doing. And the last line from skipy.endimage import convolve imports the convolve from function from the skipy library to perform convolution operations on images. So now let's go ahead. Our next step is to load a sample grayscale image. Now to do that, I can just say image equal to np.random.rand 10 comma 10. So this, what does this do? This, I mean, you can replace this with your tensor image if you have one, but this line generates a 10 by 10 random grayscale image, values between 0 and 1 to simulate an example of an image. So I'm going to go ahead and print this image. Let's look at how it looks like. I'm going to go ahead, open this and say Python day2 ex. And there you go. That's our image from 0 to 1. It had created an image for us with it's a grayscale image. I mean, I can't see it, but we can print that image using matplotlib. So what we're going to do next is we are going to visualize the effects of convolution on an image. So I have matplotlib.pyplot as plt. I have numpy. I have skipy import convolve. I already created an image. I'm going to comment this line out, and next I am going to say define convolution kernels. Now these are the filters that I was talking about. So what we are going to do here is we're going to create an edge detection kernel. So edge detection kernel by using np.array, and inside this again I'm going to go over this line by line. So first I need -1 comma -1 comma -1. Next I am gonna create another something similar. So I am going to copy this, paste it 3 by 3. So -1, I'm gonna set this as 8, -1 -1 -1. So this edge detection kernel is a 3 by 3 kernel filter used for detecting edges in the image by emphasizing high contrast area. So as you can see here, since I've selected -1, you can probably see how it automatically shows you that it is an edge detection kernel. Next, I'm going to create a blur kernel, blur underscore kernel equal to np.array, again something similar, 1 comma 1 comma 1 comma 1 comma 1 comma 1, too many commas, and third one 1 comma 1 comma 1. Pretty straightforward, right? So this is my blur kernel. Again, I'll have to divide by 9 for this is normalizing for our averaging. So this is a 3 by 3 kernel used for blurring the image by averaging the pixel values in a neighborhood. That's why it's /9. It normalizes the kernel so that the sum of all the elements equals 1, ensuring the brightness remains consistent. So that's how you create a blur kernel. Next, let's go ahead and apply convolution. Move it up. Let's say apply convolution. Now first I'm going to say edge detected underscore image equal to convolve. I will use that function that we've imported, and inside that I'll pass the image and I'll pass the edge detection kernel. Same thing I'm going to do for blurred image. I'm going to say convolve, and I'll pass the image and the blur kernel. So in this line, what we are doing is this line kind of applies the convol image kernel, applies the convolution operation on the image using the specified kernel. So first we are doing the edge detection image. So that kind of contains the result of an edge detection, and blurred image contains the result of the blur image. So once we have that, next thing I'm going to go ahead and visualize the original and filtered image. So let's display how they look like. So for that, I'm going to use again fig axis equal to plot dot sub plots. If you remember this from the yesterday's video, we kind of created something like this where I specified finally the fig size equal to 12 comma 4. If you don't remember, this what it does is the plot dot subplot creates a figure with one row and three columns for side by side visualization of the images, and the fixed size 12 by 12 comma 4 sets the size of the figure to 12 inches wide and 4 inches tall. Next, I am going to create my axis of 0 dot I am show, pass the image, and cmap equal to grayscale. So this one, along with the next one, let's create the second one and then I'll explain, go over it. Dot set underscore title. This is my original image. So now probably you got some idea. What this does is this displays the original image on the first subplot with the grayscale color map. So it takes the image and shows it in the first axis over there. Next, in my second axis, so in my second image that I'm going to show is I am show edge detected image cmap. I'm going to use the same code, so why not? The only difference is this will change to 1 set, this will edge detected. Next, you know what I'm going to do, this is for the next image where I am show the blurred image cmap equal to gray, set title equal to blurred, and then I'll say plt dot show. Now if you have not already figured out what I'm doing here, on my line number 31 and 32 I am displaying the edge detected image on the second subplot, that's why axis of 1, and on 33 and 34 I'm displaying the blurred image on the third subplot and show the final entire image here on the plot. So I'm going to go to my terminal, clear it out, run it again, and as you can see, this was the initial image that was created. This is the edge detected image, which is much similar, but if you see, there are some pixels which are a little different color because it detected an edge around there and smoothened that. And then this is my blurred image. Based on this image, it blurred it to make sure that it looks blurred consistent. So this is how you can actually take an image and then detect edges on them and also blur the images using this code. Our next step is to implement convolution in TensorFlow. So let's go ahead and I'm going to keep this code at the bottom. I'll say import TensorFlow as TF, and then I am going to create a sample input tensor and pass batch size and height, width, and the channels here. So to do that, I'm going to say image underscore tensor equal to tf dot random dot normal and pass it all the parameters 1 comma 10 comma 10 comma 1. So this is a random 10 by 10 grayscale image. So this tf dot random normal creates a random 10 by 10 grayscale, 10 by 10 because I specified grayscale image tensor with a batch size of 1 and the channel of 1. So that's what I'm doing here. Next, let's go ahead and define a convolutional layer. To do that, I'm going to say conv of conv layer equal to tf dot keras dot layers dot conv 2D. So that will create my convolution 2D. Here I am going to set my filters equal to 1. I will set my kernel size equal to 3 by 3. Always make sure that you don't add spaces here. 3 by 3. Next, this is my kernel size. Next, strides equal to 1 comma 1. Next, I have padding. These are the different parameters that we spoke about during the actual the presentation. This is my padding type is same. So what I'm doing here is I'm calling this con2d, which defines a 2D convolutional layer in TensorFlow. I'm passing filters equal to 1, which specifies the number of output channels or filters. Kernel size is 3 by 3, which defines the size of the convolutional kernel. And strides 1 by 1 specifies the step size of the convolution. And when I say padding equal to same, I'm ensuring the output size matches the input size by padding the borders. Now, if I want to get the output tensor, output tensor. So this is my where I'm applying the convolution. So tensor equal to conv underscore layer. So this is my conv layer, and I'm passing the image tensor that I've created here. So what this does is this applies the convolution layer to the image tensor. Now let's go ahead and print. First, I want to print the original shape of how it looks like. Image tensor dot shape, and then I am going to say output shape. That will be the output tensor dot shape. So that's how we do it and how to implement it in TensorFlow. Now I can also, let's go ahead and I'm going to remove this plot and just run this. Looks like I have a typo here. Yes, kernel size. There you go. Did I save it? I'll run it again. And there you go. We have the original shape 110.1 and output shape is exactly same 110.1. Just the contents might have changed because we have added the convolutional layer on top of it. Now let's go ahead and implement convolution in a PyTorch. Now if you want to display the image, you can always use this similar code and plot that image out, original image and out, and the actual image, original image and the output image. Now for PyTorch, I'm going to say import torch. Next, I want to import torch.nn as nn because that's the torch's main library. And then first I'll create a sample input tensor with my same batch size, something similar that we did with with TensorFlow channels, height and width. This is the format in which you specify. So I'm going to say image underscore tensor equal to torch, image underscore tensor equal to torch dot randn 1 comma 1 comma 10 comma 10. Again, you have to follow the same order. Batch size, channels go first, height and width go next, as compared to in TensorFlow it's batch size, height, width and channels. Next, now that I have my image, let's go ahead and define a convolutional layer. Again, I'm gonna not go over everything because it's almost same. Conv layer equal to nn dot conv 2d, and this 2d needs parameters, which is in channels, how many input channels are there, 1, how many output channels are there, I want the same number of channels. Next, I need to give the kernel size. Kernel size I've used 3 by 3, so here we just specify 3, and then stride is 1 by 1 as you just specify 1, and padding equal to same is 1. So there you go, we have the entire function written here. Con2d, there's some error, yes, comma, perfect. So now my convolution layer is, now we go ahead and apply the convolution. It's almost similar where you say output tensor equal to conv underscore layer and pass it the image tensor. Again, I think I've used the same naming, so I'm going to call it image tensor underscore pytorch pt torch dot random con underscore pt and output tensor pt conv layer pt tensor pt. So everything I'm adding pt to it just so that it makes it simple to remember. F, I'm going to say original shape is image tensor pt dot shape and output shape is output tensor pt dot shape. Go back, clear it out, run it again. So first one was TensorFlow, the second one is PyTorch. If you see input and outputs are same, if you just want to display these images, that's where you'll probably see a better display. But I would not go into details of those because it's almost same as what we did earlier. But what we can do is we can experiment with different kernel sizes, strides, and padding. So do that. Let me show you one example in TensorFlow example where my convolution layer underscore large kernel equal to tf dot kernel dot layers dot conv 2d. Just make sure you don't do typos. Filters equal to 1. I will say kernel underscore size equal to, so I'm increasing from 3 by 3 to 5 by 5 in this case. Strides, I'm going to use this same strides equal to 1 comma 1. Next is padding. I'll keep it same as input. So this is what we have specified earlier. Okay, now next step is, let's say, output large underscore kernel equal to conv layer large kernel and pass it the image tensor. And I can print this out, print f of large kernel output shape is output large kernel dot shape. Next, if I want to do the same thing for PyTorch, since I'm doing it in TensorFlow, why not also do it for PyTorch? Here's an example. I'm going to say conv underscore layer underscore stride underscore 2 equal to nn. I think the name gave away what I'm trying to do here. Dot conv 2d, and here, oops, not, it's conv 2d. You have to remember there are different functions in TensorFlow versus in PyTorch. In channels equal to 1, out channels equal to 1, kernel size equal to, I'm going to keep the kernel size same in this one, but as you saw from the name, I'm going to change the stride equal to 2, and I'm going to keep the padding equal to 1. Now you can, as I mentioned, you can try different combinations. Next I'm going to do is let's say output underscore stride underscore 2 equal to conv underscore layer stride 2, pass the image tensor pt, that's the PyTorch one, and then I'm going to say print f of stride output shape is output stride 2 dot shape. Perfect. So I have that. Let's go ahead and run this, clear this out. I could have kept it so you can compare side by side. Oh, I think it was Keras. I've used kernel. Yep, Keras, and that's why we got that error. I hope that was the only error. Let's clear it out, run it again. output shape, input now original shape for torch size, torch, and then here is my large kernel, and with that the data that I'm getting out. Stride output, I'm getting half the value of the input because it strides twice the amount, so it skips one, so that's why it's smaller output shape. So I hope you were able to follow along and get this working. Now, just to summarize, we understood the role of convolutional operations, filters, and features maps in CNNs. We learned the effect of kernel size, stride, and padding on image processing. We gained some hands on experience with TensorFlow and PyTorch for implementing these convolutional layers and developed intuition for choosing hyperparameters for convolutional operations. I hope you were able to follow along. If you had any problems or if you have any questions, do let me know in the messages and I'll get back to you. Day 3, pooling layers and dimensionality reduction. Today, let's look at in depth both of these features. First, let's start with introduction to pooling layers. Now, what are pooling layers? Pooling layers are used to reduce the dimensions of feature maps while retaining the most important information. They help make the network computationally efficient and robust to variations in the input. Now let's look at the different types of pooling. We have max pooling, which we already used. This selects the maximum value for each region of the input feature map, and it captures the strongest activations, which are the features. Then we have the average pooling, which computes the average value for each region of the input feature map and provides a more generalized summary of features. What is the role of pooling in reducing dimensionality? Now, in dimensionality reduction, pooling reduces the spatial dimensions, height, and width of feature maps, resulting in fewer parameters and faster computations. As per robustness, it makes the model invariant to small translations or distortions in the input image. Let's talk about combining convolution and pooling layers. Pooling layers typically follow convolutional layers to downsample the feature maps. This combination helps extract hierarchical features. Early layers focus on simple features, example edges, and deeper layer capture complex patterns, example objects. Now, with this in mind, let's go ahead and jump into our hands-on exercise where the objective is to implement max pooling and average pooling layers on feature maps and observe their effects on size and representation. And just FYI, we are going to use colorful images this time. So first, let's go ahead, create a new file, save it as day3 underscore ex.py. And here we'll start with importing our libraries. Our first library that we're going to import is import numpy as np, which is importing the numpy library for array manipulations. Next, import matplotlib.pyplot as plt. This is again, matplotlib is for visualizing the feature maps. Next, from skipy dot ndimage, I am going to import maximum underscore filter and uniform underscore filter. So here we are importing maximum filter for max pooling and uniform filter for average pooling from the skipy library. Next, let's go ahead and create a sample feature map. I'm going to say feature underscore map equal to np.array, and I'm going to make a random array here manually, of course, without using the random function. So 1, 2, 3, 0. Next, I'll use 4, 5, 6, 1. Next, I will use 7, 8, 9, 2. Just when you know that you can guess what I'm typing next, I change 0, 1, 2, 3. There you go. Now, this feature map that I've created, it defines a 2D array feature map as a sample feature set. It's 4 by 4 here. That's what I've used here. Now next, let's go ahead and create our max pooling, which is 2 by 2, 2x, 2x2. Let's say max underscore pooled equal to, I'm going to use my maximum filter that I have downloaded or imported. Feature map is what I'm going to pass it. Size equal to 2 and mode equal to constant. Here I'm performing max pooling with a 2 by 2 kernel size, and each region in the feature map is replaced with its maximum value. So that's what happens here. And I'm going to use next one, which is our average pooling, which is also, I'm going to do it 2 by 2. So for that, the code goes avg underscore pooled, that is my variable name, and I'm going to use my uniform filter, pass it the feature map. I'm going to pass the size, as I mentioned, is 2 by 2. So specify that 2 and mode equal to constant. So here is where I perform average pooling with a 2 by 2 kernel size, and each region is replaced with the average of its values. So now that is done, let's go ahead and plot this out. Plot. Again, I'm not going to go over this because we, I think, went a couple of days with the explanation of this. I'm going to directly go and subplot or plot my subplots, which are my images 1 comma 3 comma fig size. This is the dimensions width. I'm going to have 3 images in one row, and then my figure size is 12 comma 4. That's all I'm going to tell you now, because I think you know what I'm working on. Now for each and every images, axis of 0, I am going to say I am show the feature map, and cmap equal to, I will use viridis, VIRIDIS for this particular case, axis of 0. I am going to set the title, as this is my original feature map. Now I'm going to copy these for my second image and my third image and say 1 and 1 and 2 and 2. I am sure this one should be the max pooled and this one should be the average pooled, and I'll keep everything else except for this one is called max pooled and this one is called average pooled. Perfect. So I have that, and then I will say just show this figure. That's it. Can go ahead and run it. I can say python day 3 underscore ex.py. Looks like I have said subplot, but it's actually subplots. So sometimes you should use help from the autocomplete. It says axis 3. Did I? Oh, yeah. Again, one more typo. Run it again. And there you go. We have our 3 images, which is the original feature map that we created based on the numbers. You can probably see 1, 2. So that's why the reason we have colored is because we have used the viridis, and that makes it colorful. Max pooled, and this is average pooled. We have 3 different images based on max pooled and average pooled. So perfect. Our next step is to implement the pooling layers in TensorFlow. So how would we do this in TensorFlow? I'm going to comment this out, and in TensorFlow first I need to import TensorFlow. I've been doing some typos, so I need to be extra careful, so I'm going to go a little bit slow and import TensorFlow STF. First step, I'm going to say create a sample input tensor, which is 1 by 4 by 4 4 by, even in my comments I don't want to do any typos. This is for batch size. As you know, in TensorFlow we have batch size, then we have height, then we have width, and then finally the channels. So to display this, I am going to say input underscore tensor equal to tf dot constant and pass it feature map dot reshape and pass it those values 1 by 4 by 4 by 1 for batch size, for height, width, and channels, and then I'm going to say d type equal to tf dot float 32 because that's what TensorFlow wants. Again, what I've done here is I've converted the feature map into a 4D tensor with dimensions of batch size, height, width, and channels. Now I am going to do the max pooling on this, max pooling on that by creating a variable first, max pool equal to tf dot keras. I have to be careful what I type here. Dot layers dot max pooling to d. Perfect. And here I'm going to give a, okay, I don't think it knows my pool size. Pool size equal to 2 by 2. That's what I'll specify. Next, I need to give stride, as you remember from the previous days. Strides again, 2. And then padding equal to, I'll say valid padding. Perfect. So that's my max pool variable. Now I need to get my maxed pooled tensor. To do that, I'm going to say max underscore pool and pass it the input tensor. So first, as on line number 36, we are defining a 2 by 2 max pooling layer with strides of 2. Then we are saying max pool tensor where we apply the pooling to the input tensor that we have. Now next, do the same thing for average pooling. For that, I'm going to say avg underscore pool equal to tf dot keras dot layer dot average pooling 2d. In this case, I'm going to specify the same values, pool size equal to 2 by 2, strides equal to 2, and padding equal to valid. And then I'll say average pooled tensor equal to max underscore pool and pass the input tensor to that. So there you go. Oh, sorry, not max. Average underscore pool and pass the input tensor to that. So here what we are doing is we defined a 2 by 2 average pooling layer with strides of 2, and then we applied the average pooling to the input tensor. Now let's go ahead and print these out to see how it looks like. Say f of max pooled tensor equal to, I'll move it to next line, and inside there I'll say tf dot squeeze, call the squeeze function, and pass it the max pooled tensor dot numpy. There you go. That will give me my max pooled tensor. For my average pooled tensor, I'm going to say tf dot squeezed average pooled tensor dot numpy. Perfect. So that will give me my average pooled tensor. Now, if I want to do this similar thing in PyTorch, again, I'm going to do this and then we can see both the results. Torch, I'm going to go ahead and say print /n/n/n. So we see the difference. Torch and then import torch dot nn as nn. Next, I am going to create a sample input tensor. Again, this we need batch size. Next, we need channels, which will say 1 by 1, and then height is 4 and width is again 4. So this is the pattern for PyTorch. So you have to remember this. That's why I kind of keep on repeating these things. Input tensor equal to torch of tensor. Now here I need to give the feature map first. So I'm going to give feature map. Next time I need to give d type equal to torch format dot float of 32. Next I'm going to say dot unsqueeze. There you go, unsqueeze function, and that is 0 dot unsqueeze again of 0. So that's my input tensor. What I'm doing here is we are converting the feature map to a 4D tensor with dimensions of batch size, channels, height, and width. And then we have to unsqueeze it twice here. So next thing that I want to do is max pooling. Now for max pooling, I'm going to say max underscore pool equal to nn dot max pool, and I need 2D. So for that, and then I'll give the kernel size of 2 by 2 strides. I will give of 2. Here it's stride, not strides. So just be careful. Here is strides and here is strides. So that's why it sometimes gets confusing. Max underscore pooled underscore tensor equal to max underscore pool, and I'll pass the input tensor to it. Next, I'm going to do average pooling. For that, I'll say avg underscore pool. Now it's self-explanatory. I don't have to go over these lines. It's similar to what we did for uh, for TensorFlow. Kernel size equal to 2 and stride equal to 2. Now I'm going to say average underscore pool. So I use this PyTorch quite a lot. That's why it's much more faster for me to type these. Average underscore pool, and also Visual Studio kind of helps a little bit. Input tensor is what I pass. Now I need to pass, I need to print these things out. Let's say max pooled tensor here is not TF, but I'll get rid of all these. In here it's max underscore pooled tensor dot squeeze. Why doesn't it auto complete? Max pooled tensor, that's the name, okay, squeeze dot numpy. Okay, if it doesn't want to, that's fine. And for my average, I am going to say average pooled tensor dot squeeze dot numpy. So this looks fine, no typos, I hope. And let's go ahead and see if this displays properly. Close this out from before, clear this out and run it again. And there you go, we have the max pool tensor using TensorFlow, our max pool tensor and average pool tensor. And then we have using PyTorch our max pool tensor, Mosing, and the average pool tensor. Exactly same, but the frameworks that we use are different. Now, if you want to combine the convolution and pooling layers, let's look at an example using TensorFlow for that. I'm just going to do it for both TensorFlow and PyTorch. So let's start with TensorFlow example. Example where first I'm going to create model underscore TF equal to TF dot keras dot sequential, and in here let's go ahead and give the different layers. Again, it will give me a warning here, so I'll probably try to show you how you can change this because we have used it a couple of times before and I don't like to see warnings. 2D, I pass 32, my 3 by 3 kernel, my activation equal to ReLU, my input shape. Now again, here instead of giving the input shape in this particular line, usually what we used to do was we would say input underscore shape equal to 32 by 32 by 3, and that would be my first layer. But what I'm going to do in this particular case is here my first item, I'll say tf dot keras dot input layer in this case, and for that I will say shape equal to 32 by 32 by 3. So when I do this, I don't have to do this here. It becomes pretty straightforward and it doesn't give me a warning or error because of this. Again, not done it right. Okay, now it's right. So give the shape first, so input shape first, and then you add your convolutional layer on top of that. Next is all the same. So I'm going to say tf dot keras dot layers And this time I'm going to use a layer of max pooling 2D, and that I will say it's 2 by 2. Next I'm going to say tf dot keras dot layers dot conv 2D. Again, add a convolution conv, make sure that no typos. 64 this time, and 3 by 3, my kernel size and activation equal to again relu. Now for the final layer, I'm going to say tf dot keras dot layers dot average pooling 2D. This time I'll set 2 comma 2 same. So that's my entire model tf. Now if I want to do this in pytorch, the way to do it is pytorch example, create class simple cnn, and inside that I'm going to pass the torch dot nn dot module. Oops. And inside my class I'll define the initializer method, which is self, and here I will first call the super, same as before where you call the simple cnn and then self, and then call the initializer method of the super underscore underscore. Perfect. Next you say, oop, see typos. Next I will say self dot conv 1 equal to, in this particular case I'll say nn dot conv, I'll use the 2D, same as what we do in TensorFlow. I want to do exactly same, 3 by 3, 32 channels kernel size equal to kernel size equal to 3. So that's 3 by 3. So that's there, self dot. Next I'm going to use the pool 1 equal to, in this particular case, nn dot max pool 2D 2 comma 2. Make sure it's same as what we have above. Next I want to created a convolutional 2, which is nn dot conv 2D, and inside this I'll pass 32 comma 64 comma kernel size equal to 3. Next I'll use self dot pool 2 this time, nn dot, this time is my average pool, so average pool 2D 2 comma 2. Perfect. So that's my initializer method. Now my forward function is self comma x is the inputs that it take, x equal to torch dot relu first is what I'm going to use, and say self dot conv 1 of x, again same as what we did here. Next I'm going to say x equal to self dot pool 1 of x. So I'm going to apply the pool 1. Next I am going to say torch dot relu, and then pass self dot conv 2 that we created x. So that's the next one. And then finally the average pooling. So I'm going to say x equal to self dot pool 2 or 2x, and then that's where we return the x. Again, if you run this, it should not give you any errors, but just to be on the safer side, I want to make sure that there's no typos or errors. And first pool, second, and then no errors. Or usually what happens is, as I mentioned earlier, whatever we were doing, input shape equal to here, when we put it there, it gives you that warning. But this is the best practice that you should follow. Give the input shape first, then call conv2d. But having that here doesn't cause any harm. It's just better practice. So just to recap, today we learned the purpose and functionality of pooling layers in CNNs. We understood the trade-offs between max pooling and average pooling. We developed some practical skills for implementing pooling layers in TensorFlow and PyTorch, and we gained an intuition for how pooling reduces computation and enhances feature extraction. If you had any issues or problems while implementing this or have any questions, let me know in the messages and I'll get back to you. Day 4, Building CNN Architecture with Keras and TensorFlow. Today, we're going to jump into building a CNN architecture in Keras. Now, steps to build a CNN includes first building a convolutional layers which extract features from the input images. Next, pooling layers where we downsample feature maps to reduce dimensions and retain key features. Next, dense, which is fully connected layers, combine features for final predictions. Now, the basic CNN architecture here is the input layer goes to the convolutional layer, goes to the activation, goes to pooling, then fully connected layer, and you get the output layer. Repeat the convolution and pooling layers for deeper networks. Next, let's talk about compiling, training, and evaluating a CNN. Now, the steps involved here is first, you compile the model where you define loss, optimizer, and metrics. Next, example loss functions include categorical cross entropy, which is for multi-class classification, and example optimizers are ADAM, which is efficient optimization for large networks, and example metrics can be accuracy. Now, next step is to train the model, where we call model.fit with training data, validation data, epochs, and batch size. And finally, we evaluate the model, where we use model.evaluate with test data to calculate the metrics. Next, let's go over introduction to popular CNN architectures. We have LeNet, one of the earliest CNNs for handwritten digit classifications. Example is MNIST. We have AlexNet, which revolutionized deep learning for image classification in 2012. It was introduced ReLU activation and dropout for regularization. Then we have VGG, which uses deep networks with small filters, mostly 3 by 3, and it's known for its simplicity and effectiveness. Now, with all this information, let's get on with our hands on exercise where the objective is to build, train, and evaluate a CNN for image classification on the MNIST or Cipher-10 dataset using Keras and TensorFlow. So, for this example, let's start with Cipher-10. So, first step, let's go ahead and create a new file, save it as day4_ex.py file. Now here I'm going to first import all my libraries and go for tensorflow.keras.datasets import Cipher-10. Now this imports the Cipher-10 dataset, which consists of 60,000 32 by 32 color images in 10 classes, where we'll be dividing it 50,000 for training and 10,000 for testing samples. Next, we're gonna import from TensorFlow, I think I got the spelling right, .keras .utils. I am importing to categorical. So this imports a utility to convert integer labels to one hot encoded labels. Next, I am going to import TensorFlow itself as TF. Perfect. So I have all my imports ready here. Our next step is to load Cipher-10 dataset. To do that, I'm going to say x_train, y_train, and x_test, y_test equal to Cipher-10 dot load underscore data. So I have my data loaded here. So this loads the data set and splits it into training, which is xtrain and ytrain, and testing into xtest, ytest sets. Xtrain and xtest contain image data, while ytrain and ytest contain the corresponding labels for those images. Next step is to normalize the data. Here I'm going to take the xtrain data first, and I will run a function called as type float 32 divided by 255.0. This converts the image data to a 32-bit floating point number for compatibility with TensorFlow models, and when I divide it by 255.0, it normalizes the pixel values from 0 to 255 to 0 to 1 to improve model convergence during the training process. So I'm going to do that same thing for x underscore test equal to x underscore test as type float 32 divide by 255.0. So now once the data is normalized, let's go ahead and do one hot encode the labels. Like to put this in here. Perfect. So for y train, I'm going to say 2 underscore categorical and pass it y underscore train and 10 different categories. So I'm going to do that. I'm going to go back here and do the same thing with y test, y test. So this again converts the integer labels which we have as 0 to 9 to one hot encoding format. For example, label for 3 will become 001 0000 because it will kind of label the third element in the list as 1. And same thing for the rest of them. So now let's go ahead and print the dataset shapes. So I'm going to go ahead and say print training data shape x underscore train dot shape, and then I'll say label shapes y underscore train dot shape. Same thing I'll do for test data shape x test y test. Save it and then run it once. I'm going to say python day 4 ex.py. I'll run it. It might take some time to get the cipher data. And here we go. We have 50,000, 32, 32, 3, and label shapes are 50,000 by 10. And same thing for test data. We have 10,000 instead of 50,000 because 20% of the data, and label shapes is 10,000 by 10. So perfect. So we have our data ready. Now let's go ahead and build a CNN architecture. So for that, first I'm going to go into TensorFlow dot keras dot models. I will import something that you're familiar with, sequential. Next I'm going to go to TensorFlow dot keras dot layers and import all the different layers that I need. Convolution 2D, so I don't have to write the full length, only the name is function is good enough. Max pooling 2D, I need flatten, I need dense, and the last one is dropout. Drop out. Perfect. So I have all my functions available and ready. So next step, once we have everything, now I'm going to go ahead and build the CNN model. Now I'm going to say model equal to sequential, and here pass the parameters conv conv 2D, and then I'll pass 32 comma 3 comma 3. Now 32 is are the 32 filters of size 3 by 3, and then I need activation equal to ReLU, and my input shape equal to 32 comma 32 comma 3. Next layer is max pooling 2D, where I'm going to say 2 comma 2. So the first line adds a convolution layer with 32 layers of size, 32 filters of size 3 by C. It adds ReLU activation and input shape of 32 by 32 by 3, which is the image size and RGB channels. Next, max pooling 2D 22 adds a 2 by 2 max pooling layer to reduce the spatial dimensions. Our next one is again conv 2D, and this time I'm going to say 64 comma 64 filters 3 by 3 and activation equal to ReLU. Our next layer after this is again max cooling 2D with 2 comma 2. Our next after that is to flatten it. This flattens the 2D features map into a 1D array for fully connected layers. Now once that is ready, so I can just say use dense 128 comma activation equal to ReLU. This creates that fully connected layer with 128 units and ReLU activation. And I'll use dropout next. Drop out. This adds dropout regularization. I'm going to say with 50% dropout rate to prevent the overfitting part. And finally, I'm going to create the output layer with 10 units, one for each class, and softmax activation for classification that can be done using dense. You can say 10 comma activation equal to softmax. Perfect. So let's look at it. It all looks good. Perfect. Now let's go ahead and as usual display the model summary. So I can just say model summary. This will display my model architecture of how it looks like, of what all different table it has. Next thing that I want to do is compile the model. Now to compile the model, I'm going to call model.compile and pass it optimizer of Adam. I will give the loss as a categorical underscore cross entropy, and then metrics that I'm interested in is equal to accuracy. So that's good. That will compile. Next step is to train the model. So I'm going to go here and say train the model. Now in training process, all I have to do is like create a history equal to model dot fit, and inside this I'll pass x underscore train, I'll pass y underscore train, I will say how many epochs I want, epochs equal to 10, I will give a batch size of 64, and then I'll say validation underscore split equal to 0.2. So they should work perfectly. Next step is to evaluate the model. So I will say evaluate the test data set. For this, I can say evaluate on the test data set, not the test data set, on the test data set. I say test of loss, and I need test of accuracy equal to model dot evaluate. So that will evaluate and give me back based on x test and y test. Next, I can go ahead and print f of test accuracy is test accuracy of 0.4f. Perfect. So this will print my accuracy. Next step is to visualize the training process. For that, of course, I need to import matplotlib. I'm going to just do it here so I don't lose the frame. PyPlot as PLT. Next step, I will plot accuracy, and I'll probably plot loss here. Do it separately. I'll do it once and then copy paste, and since most of the code is same, I'm going to say plot. In this case, I have the history dot history of accuracy comma label equal to training accuracy. Next, I'm going to say plt dot plot history dot history of. Next, I'm going to use value of accuracy, and for this I'll give a label of validation validation accuracy. So I have my accuracy and my validation accuracy both displayed here. Next, I'm going to say plt dot title model accuracy, and then I'll give x label. I'll give for this its epochs of how many cycles I ran, which is 10 in this case. Y label, I will pass the accuracy. So that's what my plot will look like. Plot dot legend. Since we already gave the labels, why not plot dot show? Perfect. Can use the same thing and also plot loss. Here history dot history loss, and I'm going to call this training loss, and history dot history validation loss, I'll say validation loss, and instead of model accuracy, model loss epochs, and this is loss. And perfect. So I'll have two different plots displayed one at a time. I'm going to go ahead and clear it out and run this thing. And there you go. We have our model architecture, CN model architecture displayed here. Data shape, this we already saw earlier. And this error is same as where I do not pass the input shape first. I have to pass input shape first. But this is just a warning, so you can ignore that. I have my model architecture here. And now it's running for 10 epochs. I'm going to give it some time and come back to this. So it looks like it ran for the 10 different epochs, and then it gave me a final test accuracy of 0.6674. Here is my graph for training accuracy and validation accuracy. Looks good to me. Next, if you look at the loss versus training loss and validation loss, looks good here too. And if I close this, I have the data displayed here after each and every epoch of what the accuracy and loss was, and final loss and accuracy, and that's what was plotted. So I hope you were able to follow along and build this thing. If you have any questions, do let me know. And just to summarize, today we went into and learned how to build and train a CNN using Keras. We understood the structure and components of a CNN. We gained hands-on experience working with the Cypher 10 dataset, and we developed skills on evaluating and analyzing CNN performance metrics. So if you had any questions or had any issues, let me know and I'll get back to you. Day 5. Building CNN architectures with PyTorch. Today, we'll start with building CNN architecture in PyTorch using the NN module. The key steps here are: first, we will define a module where we will use torch.nn.module to build CNN layers like convolutional, pooling, and fully connected layers. Then we'll do a forward pass where we will define how the input flows through the layers to produce the output. And then finally, model summary will inspect the structure and learnable parameters. Next, we'll do training and evaluation of the CNN in PyTorch. In training, we will perform forward and backward passes, calculate loss, and update weights using an optimizer. Then for evaluation, we'll test the model on unseen data and compute metrics like accuracy and loss. Finally, we'll be experimenting with CNN model design and tuning hyperparameters. The different experimentation areas that we'll pick is layer depth. We'll add or remove some convolutional and pooling layers to observe the impact. We'll change the filter side. We experiment with kernel sizes, example 3 by 3 or 5 by 5. Learning rate. We'll adjust the learning rate to improve convergence, speed, and accuracy. So with all this, let's jump into our hands-on exercise where the objective is to build, train, evaluate, and experiment with CNNs for Cypher 10 classification using PyTorch. So step 1 is to load and pre-process the dataset. So I'm going to go ahead, create a new file, Python, save this file as day5_ex.py. Also, you probably saw in my folder, I already have the Cypher data downloaded from before. So I have that available so it doesn't have to download again. Close this. Now go back to my code. First, let's go ahead and import torch. We're gonna, from torch vision, I am going to import data sets and transforms. Next, from torch.utils.data, I will import the data loader. So once that is done, I'm going to go ahead and first let's go ahead and define the transformations. So I'm going to say define transformations. Now to do this, I'm going to say transform equal to transforms, which we have imported, dot compose, and my transformations can be added here. Well, I'll say transforms dot to tensor. So that's the first step. Next, I am going to say transforms dot normalize, and to this I'll give my normalization less 0.5 comma 0.5 comma 0.5 to 0.5 0.5 and 0.5. Perfect. So this is my transformation here available to use in the process when we load the data. So which is next, let's go ahead and load cipher dash 10 dataset. Now to load that, I am going to say train dataset equal to datasets dot cipher 10, the directory which I've already created, dot slash data, and I'm going to say this is training true, this is download is true. So this will run first time, and since it's already downloaded, it's not going to download anything anymore. Transform equal to transform. So I'll pass that. Next, I'm going to do the same thing for my testing data set, where I'm going to say test dataset cipher data training equal to false, because this is my testing data set. Download true, transform. Perfect. So I have my data sets available. Now let's go ahead and create the data loaders. So now to create the data loaders, first I'm going to create the train loader equal to data loader, and to that it needs the training data set. Give the training data set. I'll give a batch size. Now in this part, I'll give the batch size of 64, and I'll say shuffle equal to true for training data set. For testing loader, not data set, loader. So for testing loader, I am going to give the test data set batch size equal to 64, and I don't want to shuffle it, so I'm going to false this shuffle here. So next, I'm going to go ahead and print as usual our training data size is equal to length of train underscore dataset, and then for my testing test dataset, length of test underscore dataset. Perfect. So I have my data. Now next step is to define a CNN architecture. So I am going to move it all the way up. If you want to see this running, I can quickly run it. I'm going to say Python day 5 files already downloaded. Since we have downloaded, if you delete those files, you'll probably see it downloading. Training data size 50,000, testing data size 10,000. So everything is good. Let's go ahead and clear it out, and let's work on defining a CNN architecture. So now to define a CNN architecture, first I will create a, or let's say define a CNN model. Also, I need some imports, so I'm going to go up here, and I'm going to import torch.nn as nn. So this is the module that we need. Again, for functional, I'll say torch.nn dot functional. From functional I'll get f. So this is required. Now in here I'm going to say class CNN, and inside this I'm gonna need the nn dot module. First thing that we do is we define the initializer, function underscore underscore self. Next I'm gonna say super CNN comma self, and then call the initializer for the super class. Perfect. Now that is done. Now let's start with the layers. So first is convolutional layer 1 equal to nn dot conv 2d, get some values 3, 6 and 5. Next I'll say self dot pool equal to nn dot max pool 2d of 2 by 2. Next I'll say self dot, I'm going to give another convolutional layer, convolutional equal to nn dot conv 2d 6 16 by 5. Next I will create an fc1 self dot fc1 equal to, which is a linear model, so I'm going to say linear and pass it 16 times 5 times 5 and 120. Next I'm going to create fc2 equal to nn dot linear, and this one I'll give 120 by 84, and finally fc3 equal to nn dot linear and give it 84 by 10. Perfect. We got dot. So that's our CNN class. Next let's create the forward class or forward function. Forward function needs self and x. That's it. And here I'm going to say x equal to self dot pool and pass it. I want to pass relu as activation and pass self dot con1 of x. Perfect. Next I'm going to create another pool, self dot pool towards relu con x of 2. Perfect. Next I'm going to say x equal to x dot, let's create the view, x dot view is -1 comma 16 times 5 times 5. So I have my view for x. Next x equal to torch dot relu, another relu activated for fc1. Perfect. And of course I'll pass value of x. And now for fc2 pass value of x, and then x equal to self dot fc3 value of x. So this runs through each and every layer, and we have our forward propagation done here. Next let's go ahead and outside this let's create the model. So it's a model equal to CNN, and I'm going to print the model. Perfect. So that takes care of defining a CNN architecture. So let's go ahead and check it out. I'm going to clear it out, run python day5 ex.py, and there you go. We have our CNN model with all the different layers displayed here perfectly. As we mentioned, we wanted 3, 6, kernel size of 5 by 5, then kernel size of 2 by stride of 2. That's what we specified. So it kind of created everything for us. It's much more easier than TensorFlow, so it was easy to code this. Next step is to define the loss function and optimizer. So for that I am going to import torch dot optim as optim. Perfect. So I have that. Now I'm going to go down here, and first let's go ahead and define the loss function and optimizer. Spread is two steps. Criterion equal to nn dot cross entropy. That's the loss function that I want to use. And then for optimizer, I will say I want to use optim dot atom and model dot parameters is what I need to pass to this. And then I need a learning rate. I'll set it to 0.001. Perfect. So that should take care of it. Now let's go ahead and train the model. Now to train the model, let's create a training loop. So I will create a function. I'm going to call it train model, and it will take bunch of different parameters. First the model itself, then it needs the train loader. I have that. I need the criterion. I need optimizer, and I need to know how many epochs we want to run it for. If they've not specified any epochs, I'll just run it for 10. Now I'll say model dot train, so this puts it in train mode. And now for epoch, in range of epochs, so it will run for 10 times if not specified exactly. And here I'm going to say initialize a running loss of 0.0. And then for images and labels, in our train loader, I'm going to run a loop where it will go through each and every image. First, I'll start with the zero gradient. So this will zero out the optimizer gradient. So I'm going to say optimizer dot zero underscore grad. So this will zero out that. So next I'll do forward pass, and this will happen again and again. So outputs equal to model images, that's set to the outputs. Next I'm going to say loss equal to criterion, and then I'll pass outputs. This is to the cross entropy. I'll pass outputs and labels. Next I'm going to do a backward pass and optimize. This time I'm going to say loss dot backward, and then optimizer. I'll step up, say step, go to the next step, so that take care of that. And then at the end of it, I'm going to say running loss increment with the loss dot current item. So it will print that. I can print this for every epoch. I can say epoch is epoch, whatever the current epoch is, because it starts from probably 0, so I'm epoch plus 1, and the loss is running loss divided by length of train underscore loader. That will be my running loss, or that will be my loss here, F. So that will be displayed. Perfect. So I have that. Now I can get out of here and train the model, call the train model function. Now, do we have all the parameters? We do have the model. We have created the model right above here. And did we call it model? Yes, model equal to CNN. That's what we created. Then if you see here, it actually keeps it. That's perfect. I have the train loader. So I'm going to give that. I have the criterion. I'm going to give that. I have the optimizer. I'll give that. And epochs, I'll leave it as default to 10. So that's good enough for me. Next, before even running this, let's go ahead and write the evaluation code. So I'm going to say evaluation loop, and then I'm going to create a function called as evaluate model, and I'll pass model, and I need the test loader for it because that's where the test data is. So now first I'll have to put the model in evaluation mode. So model.eval, this will be put the model in evaluation mode. I'm going to say correct equal to 0, create to total equal to 0, and now I will loop through with torch dot no grad, starting with that, I will go over each and every images and labels in my test loader, and I'll set the outputs equal to model images. Then I don't need the first parameter of torch.max, so predicts. So second one is predicted values. I will take that from torch.max outputs comma 1. So this will give me the predicted values. Now that I have that, I'm going to increment total equal to labels dot size of 0, and I'm going to say correct plus equal to, if it's correct or not. For that I can check if predicted equal to labels. So if it's same, then I'm going to sum it where the item. Perfect. So I have that. So now I can go ahead and print it outside, where I can say f test accuracy and percentage. So I'm going to multiply by 100 times whatever the correct is, divide by total. And I want to see only two decimal places, so let's say 98.5 or 48.5, whatever it is, percentage. Perfect. So let's go ahead and evaluate the model. Say model comma, oops, and I need the test loader. Give test loader. Perfect. So now let's go ahead, clear it out and run this. Now that it's ready, it's going to train the model. It will do one epoch at a time, and it should show me as soon as it completes the first epoch, and then it will show me the loss for the second epoch. So I'm going to give it some time and wait for it. I think I gave the semicolon instead of colon, but I'll wait for it for a little while and then continue. So it took a couple of minutes, and it got us through all the 10 epochs and gave us the loss. As you can see, loss is reducing as in when the epochs increase, which means more epochs you have, less loss you'll have. And the test accuracy is 63.25%. That's what is displayed. Perfect. So that's the end of our of this code. But again, the next step is we want to experiment with CNN design and hyperparameters. So if you want to modify the architecture, for example, if you want to add more convolutional layers or change the number of filters, we can go to our model. So if you want to add another layer in here, you can add another layer and then kind of call them from here. Another option is you can adjust the learning rate. So we have a current learning rate. I'm going to reduce the epoch to 1 just now, or keep it as it is. And learning rate, if you want to change it to either add an additional 0 or reduce a 0, you can try with this, or you can even try to test with SGD or RMS pop for your optimizer, where we have optimizer Adam. So instead of this, I'm gonna comment this out, and I can say optim dot sgd, and I'll pass it model dot parameters. That's what it needs, and it needs a learning rate lr equal to, I'll say for this one 0.01, and I can say momentum is another thing that it needs. I can specify that as 0.9. That's how I can create this, and I make sure that when I'm training it, it's added as that optimizer here. Perfect. And this is how you can try with different hyperparameters, and of course it will run fine, but I don't want to run through the entire thing, so I'm going to just quickly show you. I'll run through it. It will give you the data. It will run through the epochs with the new values and then you can compare it with the previous one and see how well you have done. So as you can see, it's running through the new optimizer, and probably will have some different values, not much, because every optimizer does work in a different format. Anyways, so I hope you were able to get through this particular day and implement this. If you had any problems or issues, let me know in the messages, and I'll get back to you. And just to summarize, today we learned how to build CNN architectures using PyTorch. We understood the training and evaluation workflow in PyTorch. We developed skills in experimenting with model designs and hyperparameters, and we gained some practical experience. with Cipher 10 dataset for image classifications. So again, if you had any issues, let me know. If you have any questions about what we did today, let me know in the messages and I'll get back to you. Day 6, regularization and data augmentation for CNNs. Today we're going to look at overfitting in CNNs and methods to prevent it. Now what is overfitting? Overfitting occurs when a model performs well on the training data but fails to generalize to the unseen data. In CNNs, overfitting is common due to the large number of parameters in deep networks. Now, the methods to prevent overfitting include: we have dropout, which randomly sets a fraction of neurons to 0 during training. It prevents co-adaptation of neurons and is controlled by a dropout rate. Example can be 0.5. Next, we have batch normalization, which normalizes the input of each layer to stabilize training. It reduces internal covariate shift and allows higher learning rates. Your data augmentation increases dataset size artificially by applying transformations to images. Examples can be rotation, flipping, scaling, cropping, brightness adjustment. Let's go into the introduction to data augmentation techniques. Some of the common techniques are, as I mentioned earlier, rotation, which rotates the image by a specified angle range, example minus 30 degrees to 30 degrees. Flipping, it horizontally or vertically flips the image. Scaling, it resizes the image by zooming in or out. Cropping, extracts random portions of the image. Let's talk about implementing regularization and data augmentation in CNN training. Now, why use both? Regularization reduces the complexity of the model, whereas data augmentation increases the diversity of the training data, improving the generalization. So, with this in mind, let's jump into our hands on exercise where we will be applying dropout, batch normalization, and data augmentation to improve CNN performance. So, I'm going to start with a new file, Python file, save it as day6 underscore ex.py, and here let's start with importing TensorFlow as TF. All the libraries that I need here is from TensorFlow.keras. I need to import layers and models. Next, from TensorFlow.keras.datasets, I need to import Cipher 10. Next, from TensorFlow.keras.preprocessing.image, I will import image data generator. Next, I'm gonna to plot stuff, I will import matplotlib.pyplot as plt. So okay, once I have that, next step is to load and pre-process the Cipher 10 data. So first, let's go ahead and load the Cipher 10 dataset. To do that, I'm going to create x underscore train, y underscore train, comma, x underscore test, y underscore test, and this I'll get from Cipher 10 dot load underscore data. Perfect. Once I have the data, let's go ahead and normalize pixel values to the range 0 to 1. So currently they are in from 0 to 255. I'm gonna normalize them from that to 0 to 1. So I'm gonna say x train equal to x underscore train dot as type, needs the type of float 32 divide by 255.0. Same thing I'll do for x test as type, float rate to 255. Perfect. Now for the features or the labels, I'm going to say one hot encode the labels. So for that, I need ytrain equal to tf dot keras dot utils dot to underscore categorical and pass y underscore train comma 10. Same thing I'll do for test y test tf test comma 10. So perfect. So we got everything, whatever the numbers were there, they're all into zeros and ones into a list of items from 0 to 1. So for example, 3 is decoded as or encoded as 0 comma 0 comma 0 comma 1 comma 0 comma 0 comma 0. So for the 10 of them, they're kind of the right index is picked for that particular item. So 0 to 9 we have items, and that's how it will pick. Next, let's go ahead and apply data augmentation. So do that. I'm going to say data gen equal to image data generator. I've already imported that. And here I'm going to do some random rotation. So I'm going to say rotation underscore range is equal to 15 degrees. Next, I can say width shift range can be from 0.1. This will do the horizontal shift. Next, I can say height shift underscore range equal to 0.1. Again, this do a vertical shift. And then I have horizontal flip equal to true. So this will do horizontal flipping of the image and create new images or data set for us. Now I'm going to say fit the generator to training data. That I can do by saying data gen dot fit to my training data, which is x underscore train. Perfect. So that once that is done, our next option is to build the CNN model with dropout and batch normalization. I'm going to scroll up a little bit here and then create a function, call it def create model. And in here, I will say model equal to models dot sequential. It's the one that I need. Now, first thing is let's add the convolutional layer 1, but before that, let's give that input shape. So I'm going to say model dot add, and I'm going to say layers dot input, and the input shape that I give is 32 comma 32 by 3 classes. Next thing that I can do is now I can give the convolutional layer add layers dot conv 2d 32 filters and 3 by 3 and activation equal to relu, and I don't need the input shape because I've already given that, so this is good. Model dot add, next one I'll give a layer for batch normalization, so that is batch normalization. Perfect, so that's done. Next, oh, I don't have to add commas because this is not inside particular instance. I can just say keep on saying model dot add. Next one I want to add again convolutional 2D. I will say convolutional 2D 32 3 by 3 activation equal to relu. Next I'm going to again do batch normalization. Next I'm going to add max pooling. So I'll copy this and say instead of this I'll say max pooling 2D, and that needs 2 by 2. Perfect. So that closes this. Is it all closed? Yeah, perfect. So I have 3 brackets, 2 brackets in front. Perfect. Next one, I want to do model dot add. I want to add the dropout layer here. So I can say layers dot dropout, and that is drop out and I can give a value of 0.25, which is 25%. Next, I'll create another convolutional layer. So I'm going to say model dot add. So what I'm going to do is I'm going to copy this entire thing for the second layer. Model dot add. I don't have to add this input. Convolutional 2D 64 by 3 by 3 activation equal to ReLU batch normalization. Again, I'll say 64 3 by 3 activation ReLU batch normalization layers max pooling 2D and then dropout of 25. Perfect. Next, so I'm going to kind of mention here that this is convolutional layer 1 and this is our convolutional layer 2. Now I will create a fully connected layers. To do that, I'm going to say model dot add. I'll have to first add the flatten. So I'm going to say layers dot flatten. Next, I'm going to say model dot add, and this time I'm going to add a dense layer 512 comma activation equal to ReLU. Next one, I'll add the batch normalization to this. Batch normalization. Next, I'm going to add a dropout of 0.5. Next, I'm going to create another dense, which is the final output layer, dense with 10 different classes, and activation I'll use softmax. See, activation is all spelling is right. And then finally, I will return the model from here. So that kind of builds my model. Now that my model is ready, let's go ahead and compile this model. To do that, first get the model. I'll say model equal to create model. This will create our model. And then I'll say model dot compile, and I'll have to specify optimizer equal to, I am using Adam. I will say loss equal to, I will create the categorical underscore cross entropy. Next, I will say the metric that I'm interested in is accuracy. Perfect. So that will compile my model. Now that it's compiled, let's go ahead and train the model using the augmented data generator. Now to do that, I'm going to say create a parameter history equal to model.fit. The reason I'm doing it is so I can plot these data in a little while. Data gen dot flow, I'll call x underscore train comma y underscore train, and I'll say batch underscore size equal to 64. Next, I'm going to say number of epochs that I want to run it for is 20. It's going to take forever to run this, but I will take that chance so I can get some good data out from here, or get good model out of here. Y underscore test, my validation data comes from there, and then I'll say steps per epoch equal to x underscore train dot shape of 0 slash 64. So this is steps per epoch that I want. Next, let's go ahead and evaluate the model. So based on the test data that we have, I can say test loss comma test accuracy equal to model dot evaluate, and I'll pass it x underscore test, y underscore test, and verbose equal to 2. Next, I'm going to go ahead and say print test accuracy is test underscore accuracy 0.2 f. So that will display my accuracy. Now let's go ahead and visualize I want to do everything together because it's going to take forever to run this code. So let's go ahead and visualize the training and validation accuracy. So I'm going to say plot history dot history of accuracy, comma, I can say label equal to training accuracy. Next, I'm going to plot. Uh, now that I have accuracy, next is validation accuracy. So I'm going to say validation accuracy, and this is validation accuracy. Let's move it up. So I have that. Next, I need to get the X label. So I'm going to say plt dot X label. I will specify that that's epochs, and my Y label, that will be my accuracy. Next, I'm gonna give a title, and that title will be training and validation accuracy. Next, let's show the legend and then show the plot. And again, for my loss, I'm going to copy this, paste it here, say loss. This is training loss. This is validation loss. So this is validation loss, epochs, accuracy. No, this is loss, training and validation. So looks like I have everything here that I need. Hopefully there's no typos, but we'll come to know. So I'm going to go ahead and run this code. I'm going to say Python day 6 and run it. As you can see, probably it will take some time to start up because cipher data is pretty, and as it looks like I have some error here, layers input. Oh, I forgot to mention shape. So I have to go here and say shape equal to, that's how you specify, layers.input shape equal 32 by 3. So let's go ahead and run it again. Let's clear it out, run it again, and it ran. It gave some warning about the pi data set, which is not something that I'm using, but it's a built-in function. But it's running our epoch 1 and it's going to run until 20. So I'm going to go ahead and pause it a little bit, pause here, and then come back and start recording once it's completed. So it took some time, but here it went through all the 20 epochs. There were some errors in between where it ran out of memory. But again, we have our graph here which shows the training and validation accuracy. As you can see, as and when we train more, the accuracy is increasing. Similarly, we have our training and validation loss, where depending on how much training we do, it kind of keeps in reducing the loss. So there you go, perfectly trained, perfectly. And that's our project, where today we learned and understood how dropout and batch normalization prevents overfitting in CNNs. We learned to apply data augmentation techniques to enhance model generalization. We gained practical experience implementing regularization and augmentation in TensorFlow, and we developed intuition for experimenting with regularization rates and augmentation strategies. I hope you were able to follow along. If you have any questions or had any issues while implementing this, let me know and I'll get back to you. Day 7, CNN project. Image classification on fashion MNIST or Cipher-10 dataset. So first, let's look at applying CNN architecture on a larger dataset. Now, why larger datasets? Larger datasets like Cipher-10 or Fashion MNIST represent more realistic and diverse challenges compared to toy datasets like MNIST. They require deeper architectures, careful regularization, and augmentation for optimal performance. Next, experimenting with architecture design, regularization, and augmentation. Now, some of the key techniques to improve this performance is first, architecture modifications. Add more convolutional layers or change your kernel sizes. Use more filters in deeper layers to capture complex features. Regularization. Apply dropout in dense layers and batch normalization in convolutional layers. Prevent overfitting in deeper models. Data augmentation. Use techniques like random flipping, cropping, and rotation to improve generalization. Let's talk about analyzing model performance and tuning. So, the evaluation metrics that we use are accuracy, which is for overall classification correctness. We have loss, which measures the difference between predictions and ground truth. Confusion metrics, which highlights misclassified classes for deeper insights. So, with all this in mind, let's jump into our hands on exercise where we will be building, training, and optimizing a CNN for, in this case, we'll use Cipher 10 image classification and experimenting with regularization and data augmentation to achieve the best performance. And I would recommend you try out to work with the Fashion MNIST dataset to do the same. So first step is to load and prepare the dataset. So I'm going to go ahead, create a new file, save as day7 underscore ex.py. And as you can see, I already have the data downloaded, so I don't have to download again. In here, first I'll start with importing torch. Next, from torch vision, I will import the data sets and transforms. Next, from torch dot utils dot data, I will import data loader. There you go, I have that. Next, let's go ahead and define transformations with data augmentation. So for that, I'm going to say transform underscore train equal to transforms, and here I'm going to compose, and my data set that I want here is, first I will say transforms dot random horizontal flip. Okay, I think I'll have to random horizontal flip. Next one, I'm going to say transforms dot random crop, and this time my crop will be 32 by padding equal to 4. Next, I'm going to say transforms dot to tensor. So it doesn't show up, so I will to tensor. I think I misspelled, that's why. This makes sense. Next, I will say transforms dot normalize, and this time I'll give some parameters 0.5 comma 0.5 comma 0.5 and 0.5 comma 0.5 comma 0.5. Perfect. So I have my data set here, my transform here perfectly created. Let me cross check one more time. Random horizontal flip, transform dot random crop, 32 padding. So given additional data augmentation here. Now let's go ahead and create another transform test. Transforms dot compose, and this one I will create, let's say transforms dot to tensor. So this is for my test data set, that's why it's called that, and I need normalize because I need to normalize the data too. I'll give the same values. Perfect. Now next step is to load the Cipher -10 data set. To do that, I'm going to say train data set equal to datasets dot Cipher 10. Similarly, I mean, you can use fashion mnist also that is available. So I'm going to use cipher 10 right now. The data where I want to save it equal to dot slash data, which I already have it, so I don't have it will not download again. Train equal to true, download equal to true, and transform equal to, I already created the transform train, so I'm going to use that transform. Where is it? Transform train. Perfect. Copy that. I'm going to use the same copy paste, and instead of train I'll say test. Cipher train equal to false, download true, and then this is again test. So is it not transform test? Oh, it's transforms. That's why it was causing. Let me fix that. Transform train and transform test. So perfect. So I have both of them. Now that I have my data set, next thing to do is get the loaders. So I'm going to say train loader equal to data loader, and pass it the train data set. Say batch size equal to, I'll say 64, and I'll say shuffle equal to, since it's training, I'll say true. But for the test loader, data loader, I'll give the test data set 64, shuffle equal to false. I don't want that to be shuffled. Perfect. So I have my data set here, my loaders here. Next, let's print it. Print f of training data size. Just to check the size, I am going to say length of train data set. Same thing. Test data set. I'll say test data set, length of test data set. Perfect. Now I have that. Next step is to define the CNN architecture. So this time I'm going to call it the enhanced CNN. Also, I need some more imports. So I'm going to say import torch.nn as nn, and import torch.nn.functional as f. So with that, let's go ahead and let's create a class which is enhanced CNN, not the usual CNN that we work on. And n.module is what I'll pass as a parameter to this. I'm going to create the initializer method as usual, init underscore underscore. You can kind of copy paste this from one of the previous projects if you want to do it faster. But again, I like to practice, as I say always. That makes you better in coding. Init underscore underscore, call the, so this will call a super method. Next, I'll give my first convolutional layer conv1 equal to nn dot conv2d, and then to pass it parameters 3, 6, and 5 are standard numbers. Next, I'm going to say self dot bn1. This is our batch normalization. So I'm going to say nn dot batch normalization 2d, and I'll pass the value 6. Next is my second convolutional layer conv2 equal to, in this case I'll say nn dot conv2d and pass 6 comma 16 comma 5 based on the previous layer. Next one is bn2 equal to nn dot batch normalization 2d, and this time I'll pass 16 based on the previous layer. Next, I'll create my pool equal to nn dot max pool 2d 2 by 2 self dot dropout equal to dot dropout, and this I'll give 50%, so 0.5. Next, let's calculate the size of the output from the convolutional layers dynamically. That I can do by saying self dot underscore calculate underscore conv underscore output, which will be another function that I'll write. This will be helpful to kind of pass it to our fc1, where I can say self dot fc1 equal to nn dot linear, and I'll pass self dot conv underscore output underscore size comma 120. Before we used to like assign it, but we are calculating it just so that it's not it's generated dynamically. Next, fc2 equal to nn dot linear, and this time I am going to assign this 120 comma 84 based on the previous input. Self dot fc3 is equal to nn dot linear 84 comma 10 based on the previous input. This is my final layer for 10 classes. Now let's go ahead and define that class to calculate the convolutional output. So for this, I am going to pass the parameter of self, and here I'm going to create a dummy input tensor with the same size as the input images first. So I'm going to say dummy underscore tensor, dummy underscore input equal to torch dot zeros with 1 comma 3 comma 32 comma 32. So that's the entire batch size, channels, and height and width. Now with torch dot no grad, I will produce the output, which is self dot pool of f dot ReLU, self dot bn2 is the next one, with self dot conv2 with f dot ReLU with self dot bn1. It kind of becomes too complicated depending on how many layers we have. Conv1 with dummy input in there. So let's make sure that all these brackets are properly closed. As output equal to self dot pool f dot based on the data here, ReLU self dot bn2 con2 ReLU self bn1 con1 of dummy input. Looks fine to me. Let's see if there's any issues. We'll get an error. Convolution output size equal to output dot numeral. That's the function that we call to get the values. So we have that. Next thing is, let's create the function, the forward function, which takes self and the value of x. So for this, I'm going to go ahead and first say x equal to f dot ReLU of self dot bn1 of self dot conv1 of x. That will give me my x equal to self dot pool. Next is the pool part, where we have f dot ReLU of self dot bn2 of self dot conv2 of x. So that's my second. Next is x dot view. This is for flattening the tensor dynamically. I'm going to use x dot size of 0 comma -1. Perfect. Next I'll say x equal to f dot ReLU of self dot fc1 of x. Now once I have that, I can use the dropout next. X self dot dropout of x. Next I'm going to say x equal to f dot ReLU of self dot fc2 of x. Next I'll say x equal to self dot fc3 of X, that's my output layer, and that's what I'll return back, X. So I have all of them based on this here. Hopefully, if not, I'll come back once the error shows up. So next I'm going to say model equal to our enhanced CNN model. Let's implement that and then print this model out. Now I should not get any errors, but I can check quickly. Python day7 ex.py. Let's see. Oh, I think I spelled zeros wrong, and that is right here, zeros. Let's go ahead, clear this out, run it again. It says output is not defined. Look, okay, equal to, so that's where I'm defining output. Perfect. So let's go ahead one more time. Let's hope there's no more typos. And there you go. We have our enhanced model displayed, and it ran through the entire thing and printed the model. Perfect. Our next step is to train the model. So let's go ahead above here and let's import torch.optim as optim. Once that is done, I'm going to come down here. After I print the model, I'm going to go ahead and define the loss function and optimizer first. Define loss function and optimizer. To do that, I'll say criterion equal to nn dot cross entropy loss. That's what I need. Next, I'm going to say optimizer equal to optim dot, I'm going to use Adam optimizer, and I'll pass it model dot parameters, and it needs the learning rate. I'll give 0.001. So I have my ready. Next, I'm going to create a training underscore loss list, empty list. Here, let's move it all the way to the top. Now let's create our training loop. So training loop. Inside my training loops, look, first let's define the function train model, and this model I'll pass model. I'll pass the train underscore loader. I will pass the criterion. I will pass the optimizer, and epochs I can set it to 20. Again, it's going to take a lot of time, but I'll take the risk. Model dot train, which starts our training the model steps, and here I am going to say for, here looks like, since I again used dash, that's why it was giving me an error. Now going through all the images and labels in train loader, there's the first step. Oh, before that, let's run for each and every epoch. So I'm going to say for epoch in range of epochs, I am going to say running loss equal to 0.0. I'll initialize at 0.0. Then I'm going to go over each and every image and label in train loader. I'm going to say optimizer dot 0 underscore grad. So I'm going to zero out the gradients. I'm going to say output equal to, or outputs equal to, again, model dot, or model of images. Next, I need the loss is criterion, and I'll pass outputs and labels to it. Next, I need to step, we want to go backwards. So I'm going to say loss backwards, so backward propagation after that. And then I'll say optimizer, I will go step up. That's it. Next, I'm going to increment the running loss after all my steps are done here. So loss dot item, that's my loss. Next, I'm going to go outside and say epoch loss. I think that's what we had. That was what we need, is running loss divided by length of our train loader, which is the reason I'm doing that is I can get my training loss dot append. I can append it in there. That's why I created that. I can also print it out like how I did last time, where it will show me every single time which epoch it is. And inside that epoch, since it starts with 0, I'll say epoch that loss is epoch loss with only 4 decimal places. Perfect. So that's done. Now I'll go ahead and call the train model function and pass all the things that it needs. I have model, I have train underscore loader, I have the criterion, I have the optimizer, and I'm not going to give epochs because by default it's 20, so I'll keep that 20. Next step is to evaluation of this loop, write the evaluation loop for this model. So I'm going to go ahead and write that function evaluate underscore model. For this it needs model and test loader, and I'll say model dot eval. So it starts the evaluation process and set correct equal to 0, and what is the other one, total equal to 0. These are two parameters that we initialize, and we will increment or decrement depending on the data that we get with torch dot no grad. So we'll start with empty grad, and then for images and labels, now this time in test loader. So I'll take each and every one and then check for the outputs equal to model images. So this will give me the outputs of those. I don't need the first parameter of this, but I need the second one, which is predicted. So I'm going to say torch dot max of outputs comma 1. So that will give me the predicted values. I'll say total plus equal to labels dot size of 0. So that will give me the total increment, and correct increment will be predicted is equal to labels. If it's equal to labels, what I'm going to do, sum of item, that's what I'll do. So that will give me increment my corrects. Next, go outside and print my test accuracy. Test accuracy is, I want it in percentage, so 100 times of correct. Did I spell correct wrong? Nope. Correct divide by total 0.2f percentage. Okay, so that is good. Now let's go ahead and evaluate our model, and I'll pass it model and test loader. That's all it needs. Perfect. Now if you want to plot this, we'll have to first import matplotlib as pyplot as plt. I usually like to put my imports up, but for this I'm just going to keep it here and make it simple plot. So first I'll say plot training. Now we'll take the training loss and I'll use the label equal to training loss. Next, plot dot title, I'll create the, call it loss curve. Next I want to give the x label, which is epochs, which is 20 in our case, and then plot dot y label, which is loss in our case. Next I'll say plot dot legend. Perfect. And then plot dot show. Perfect. So that kind of completes our entire exercise. I hope you were able to follow along, and if not, just pause it wherever you can and go through it. That's what I would say. Next, now let's go ahead and run this. I'm going to go here, clear it out. It's going to take some time because I have 20 epochs to run through. I have the data. Okay, it looks like there is some, instead of relu, I have said rel. So let's fix all these things. f.relu, where is f.rel? Here. Perfect. Clear it out. Let's see if there's any more errors. I like to do one error at a time, even if it shows me 20 errors. But as long as it shows me that it's going through epoch 1, I think that's probably the start of it. And that's what I'm waiting for. Since the data size is big and it's going through that entire data set and testing it out, the epoch will take some time to show up. But this delay kind of gives me, as you say, as I said, if more and more time it takes, that means it's working. There's no error. So that's good. So I'm going to stop here for a little while and come back once it's completed. So here you go. After the 10 epochs that we went through, it reduced the loss. As in, you can see it, test accuracy is 62.25, and you see the loss curve here keeps on going down as and when the epochs increase. So this is good sign. I'll close this up, and this is our data. If you had something similar, that's good. If not, let me know, and I can help you out on how to fix that. So just to recap, this week on week 10, on our day 7, we gained hands on experience building and optimizing CNNs from practical datasets. We understood the importance of regularization and augmentation in improving the model generalization and developed skills in analyzing and tuning CNN performance and prepare for real world scenarios requiring robust model training and evaluation based on the dataset that we have seen. So I hope this was helpful. If you have any questions or had any issues, let me know in the messages and I'll get back to you.